Now, under the plug-and-play algorithm, low-rank tensor optimization with non-local plug-and-play regularizers or snapshot compressive imaging. Here, the increasing volume of hyperspectral images brings great challenges to storage transmission. Recently, snapshot compressive imaging (SCI), which compresses 3D HSI into 2D measurements, has received increasing addition since original HSI can be naturally represented as third-order tensors. In this work, we reformulate the T-gradation model in SCI system as a tensor-based form, which differently allows us to explore the underlying low-ring tensor structure of HSIs that address the Hill-Bosed SCI reconstruction problem. We suggest a global rank tensor optimization model with a non-local plug-and-play. A non-local plug-and-play is a very important part. Regularizes GNLR to construct the HSI from the 2D measurement, which is flexible and collaboratively integrates three-directional tensor nuclear norm 3D-TNN and two implicit non-local regularizers. More concretely, 3D-TN characterizes the global correlation of the underlying HSIs. Two implicit regularizers under the PnP framework exploit the benefits of the transform dispairs and low rank periods on similar patches of the coefficient tensor respectively. Based on the alternating direction method of multiplace algorithm, we develop efficient algorithm to tackle proposed model. Extensive experiments remotely sensed HSI's real-world HSI demonstrate the superiority of the proposed GNLR method. That's why here low-rank tensor optimization with the non-local plug-and-play regularizers for snapshot compressive imaging. Index terms alternative direction method of multipliers ADM alternative direction method of multipliers hyperspectral imagery reconstruction and plug and play snapshot compressive imaging three directional tensor nuclear norm 3D TNN. Hyperspectral images are naturally third-order tensors of 1D spectral and 2D spatial information for the high-resolution spectral information of HSIs. They have widely employed in many fields such as resource direction, target direction, and environmental monitoring. However, the extremely rich data information leads to waste storage occupancy, which is not convenient for subsequent applications such as classification, normally direction, unmixing, and efficient compressive mechanism with a reliable reconstruction method is essential. Based on the compressed extensive theory, many compressed measurements have been proposed, one of which, with promising applications, is snapshot compressive imaging. The SCI system samples a set of contiguous channels, example coded aperture compressive spectral imaging channels. So imaging classic C for coded aperture A compressive spectral imaging to obtain 2D compressed measurements, greatly reducing the computational workload to reconstruct an HSI from 2D measurements. Various methods have been proposed. These methods can be divided into two categories. First one is deep learning, second one is deep learning based method and model based methods. Based method and model based methods. In deep learning, based methods mainly develops the existing networks to reconstruct decided HSI from the 2D measurement. For example, we have it integrated the unit at the self-attention generative adversarial network to exploit the non-local correlation of the HSI. Ma et al. Developed the traditional alternating direction method of multipliers. Alternating direction method of multipliers algorithm into deep neural network, unfolding inference iterations. The deep learning based methods need numerous data to pertaining the neural network, and it is difficult to obtain extensive training data. Moreover, the network is usually limited. The network is usually limited to the capacity generation, since the network trained by a specific dataset probably does not satisfactorily reconstructed results on other datasets, especially for remotely sensitive HSIs. The model-based methods do not rely on training data and thus avoid aforementioned shortcomings in deep learning-based methods. The key to ensuring the reconstructed results of model-based methods to reasonably extract useful features such as sparsity, local smoothness, and non-local self-similarity (NSS). Non-local self-similarity to capture the sparsity of the original image. Young et al. Proposed at 25th paper proposed the Gaussian mixed model. Moreover, Yuan et al. In 16th paper proposed a generalized alternating projection based total variation gap TV method and solved this problem by generalized alternating projections. In 26th reference algorithm, since GMM in 25th reference paper and the cap TV in 26th paper capture the sparse period of the underlying HSIs. These methods provide unsatisfactory reconstruction and reconstructed result. Example, over smooth phenomena. Recently, Liu et al. At 27th references proposed a decompressed DEC-SCI method capture the low ranks of the image. More concretely, this DESI method clusters spatial similar 2D patches into groups by the NSS of HSI and exploits the low rank property of these groups. However, directly grouping similar patches in the original image is time consuming and band-wise calculating neglects the spectral correlation at the 28th reference of the target HSI. To tackle these problems, he et al. 29 proposed at 29th reference proposed a non-local meetings global NG-meet restoration paradigm to exploit the NSS of coefficient tensors under the matrix factorization. The matrix factorization usually unfolds the third order tensor as a matrix along the spectral dimension and then factorizes the matrix into a semi-orthogonal basis matrix and a coefficient matrix. On the other hand, NG-meet explorates the NSS of the coefficient tensor rather than the original HSI, which reduces the computational complexity. On the other hand, the method captures the low rank property by the matrix factorization, but it fails to maintain the whole structure a third order tensor. To solve the aforementioned shortcomings, we simultaneously characterize a tensor-based low rank period and two non-local periods. Considering the fact that the matrix factorization destroys in the invariant structure of a third order tensor, we use three-dimensional tensor nuclear of 3D TN, three-dimensional tensor nuclear now in reference number 30, which has achieved great success imaging denoising to maintain the global structure underlying HSI. Since the coefficient tensor inherits the non-local properties of the original HSI, we utilize the implicit regularities, that is weighted nuclear norm minimization, WNM and block matching and 3D filtering PM3D in 32. Under the PnP framework, to flexibly and efficiently capture the non-local low rankness and the non-local sparsity of the coefficient tensor with lower time consumptions. Based on the above prior knowledge, we suggest a global low-rank tensor optimization with non-local plug and play regularizers. Then G for global, N for non-local, LR regularizers non-local NL. Concept HSI from measurements. The GRI simultaneously characterizes three period information: global rankness, non-local transform sparsity, and non-local rankness. See figure 1. The contributions of this article include three aspects. What is the three aspects? And then for this figure 1, global rankness, global period, original image, N1, N3, N2, global period. In global rankness, singular value, N2 and 3, slice 2 minus N. Here, minimum N and N, slice 2 for 2 minus N2. Here like this. Okay. Here, minimum of N1 and 2, slice 2 to N3. This one. This